reflection across the x-axis. There we go. So we'll look at number 11, reflection across the x. And again, with all of these reflections, any of the transformations, we're always going to go back with what our setup was. So reflection across the x-axis is our negative f of x.
This one, I think 1.4. But can you tell me which ones we did? Because I feel like I did.
Because I can look it up here in a second. So negative f of x. Three through 9 and 11. So we have negative. Now we're going to replace our function since we still have just f of x. We're going to replace it with the function it gave us. So it gave us f of x as negative 5x plus 2. Now at this point here, we're going to distribute the negative. And our negative times negative 5x is going to make it positive. And negative times our positive 2 would be negative 2. And that would be our reflection across the x-axis. Does that answer that question? Now, if it was across the y, it would end up just being 5x plus 2 because we just replaced the x with the negative x, and it doesn't affect the 2. Any other questions? Okay. What we're looking at today is systems of equations with 3 variables. Systems of equations with 3 variables. Systems of equations with 3 variables. Now, you've done systems of equations before. It's just been a while since you've done them. Because in Algebra 1, y'all did systems of equations with 2 variables. You picked one with using elimination, eliminated it out, solved for the other, and then went from there. Or substitution, you got one of the equations as y equals or x equals, plugged it into the other equation, and then solved for the other variable. But in any of these here, with solving systems of equations, all of geometry, all of Algebra 1, at most, we only solve for one variable. Because even if we had an equation that had 2 variables, we had to solve for one first so that we could find the other. We never solved for 2 variables simultaneously at the same time. And the same thing is true for this here. Now, we will have 3 equations. We can have 3 equations with 3 variables. It is possible to solve a system of equations with 3 variables, but only having 2 linear equations. But we won't look at that here. That is, again, we'll come back to it in pre-calculus or college algebra and have those. But we get to those there.
If we do pre-calculus, will that count?
Yes. Your 3rd math credit. College algebra is the only class that we offer here besides AP.
So we don't have to do it in college?
Pre-calculus, no, but you will have a math credit in college that you need to take. College algebra or another kind of math class. I mean, besides the math majors, I mean, there's statistics.
You only have to have one.
But I would check into the university to see what they say that you need. Now, most systems of equations, if they have a solution, it is an ordered pair. It's x, y, z, an ordered triplet. Now, whenever we list out the solution as an ordered triplet, the x value goes first, y goes second, z goes third. Is the order that we list it. Now, there's 3 different setups that we can have. The first one is that we have exactly one solution. And a 3-variable system or 3-variable linear equation is a plane. Kind of like a sheet of paper. It's a plane that extends indefinitely in all directions. And where the 3 systems or the three equations intersect would be the solution. This would be our ordered triplet, x, y, z, would be this point here. Whenever we have a single solution, exactly one solution. Or we can have infinitely many solutions. Now notice that this says infinitely many, not all real. There is a set line or plane that the solution is true for. Now, we're not going to do it in here, but definitely in the pre-calculus course in college algebra, we actually define what this system is. And one of them could be 2a, a minus 4, and a. Could be a solution to the system for any value of a. So if we just put in a value for a, I'm just going to pick a random value, and I said 3. 2 times 3 is 6. 3 minus 4 is -1, so 6, -1, 3 would be a solution for this system that worked. And we could find any value of a that would work for it. So there are an infinite number of solutions because there are an infinite number of values for a that we could plug in, but it's not all of them because there are still some points that don't work because a point over here would not work for the system. Questions on this so far? Because we could have one, we could have infinitely many, and I think y'all can take a guess at what the third one is. No solution. Now the first two, this line here and these here, we do have two of the planes crossing. We have points that would be true for two of them, but they are not true for all three. For a system to have a solution, it has to be true for all three equations. Even the second one, we do have points of intersection, but it's not points of intersection for all three. And the last one, none of them intersect. They're all parallel. If we get one of these three cases, or a setup that would, if graph would look like one of these, it's going to be no solution. And specifically, if we end up, as we're solving it, get one of the equations to this point here, 0 equals 1, we get a false statement. Most of the time it'll be 0 equals 1 or 0 is equal to some number. We're going to get a false statement. So it's going to be no solution. And if we get that at any point through the solving process, no solution, we're done. However, if you obtain a true statement, such as 0 equals 0, 2 equals 2, then most likely it's going to be infinitely many solutions. Now they do have these steps here. These are listed in your note sheets on top of the back of the first page. And when we look at this first one here, we can do those, or kind of, as I say, the first main step is to pick a variable to eliminate. And an eliminator equation. You can, it is following those steps that we have there. I wouldn't write it next to the problem. So you can write it on the first page, but these are the steps we're going to use. Yeah. And for the most part, especially when I solve these systems of three variables, I don't use substitution. It is possible to use substitution, but I stick with elimination. Now what this means, pick a variable to eliminate in an eliminator equation, is we look at this one here. We'll look at this one here to see this. We're trying to see which variable can we eliminate or make be the same, all of them be the same, or same as the other two, easily. And if we look at x here, eliminating x out, I look at the smallest one, so 2x, because we have 4x, 2x, and 6x. So looking at 2x, can I easily, with multiplication, turn 2x into 4x? Well, yes, because if I want to turn 2x into 4x, we multiply it by what? 2. And now they're the same and we can eliminate out. The same thing with 2x and 6x. Well, I can multiply 2x by 3 and it becomes 6x. I can easily turn 2x into 4x and 6x. So we could choose x to be eliminated first. Let's look at y next. We have 2y, 3y, and y. Well, the small one is 1y. Can we multiply something by y to get 2y? Well, yeah, it would be 2. What can we multiply by y to get 3y? 3. That's pretty easy to make them be the same, and we can eliminate y out. Let's look at z. Well, the smallest one for z is 3z, yes? What can I multiply 3z by to get to 4z? Guys, what can we multiply 3z by to get to 4z? Is there a nice number that we can do that by? Guys? Well, not really. Because to get those to be the same, I'm going to have to multiply 3z by 4 and 4z by 3. There's a little bit more to it, and especially with 5. So if we look at these here, when I'm picking a variable to eliminate, an eliminator equation, well, here, the easiest ones are x or y, because I can easily make one of the equations into the other two. Can y'all see that there? So we're picking a variable to eliminate, an eliminator equation. We're trying to see, is there one variable in one of the equations I can turn into the other two? Do we want to eliminate x or y first? Because either one of those will work. Y'all pick x or y. X. So we're going to pick x to eliminate first. That is what we're doing first. We're going to eliminate x. Now we need to pick an eliminator equation. And all that means is we're going to pick one of these three equations to eliminate x out of the other two. And whenever we do this, I will always pick the equation, guys, with x has the smallest number, the one that's easier to turn into the other two. And that's going to be our middle equation. Because it's going to be easier to turn 2x into 4x and 6x than it is to turn 4x into 2 and 6. Questions on this so far? Because once we've picked our eliminator equation and variable we're going to eliminate out, we're going to eliminate it out of the other two. So I would pick a spot on the page that we're going to work this out and leave space on either side to actually do our scratch work, because we will have some scratch work here. I'm going to write these in the dead center. You can write them in the dead center or off to the left, off to the right. And then I'm going to do the work on the sides. So the first thing I'm going to do is just rewrite the other two equations. So we have 4x plus 2y plus 3z equals 12. Yes. So I write these two out. All right. Yep. Because what we're doing here is we are turning three equations, because we're given at the start three equations with three variables. Now, as I said at the start, we can't solve for multiple variables at once. We can't do two variables at the same time, let alone three. So what we're using this eliminator equation to do is to eliminate one, so that we go from three equations with three variables to two equations with two. And then from there, we're going to go from two equations with two variables to one equation with one. So that's our goal. Now, the first thing we're going to do is remove x. That's what we're trying to do, is eliminate x. Now, we set these two aside because these are the two equations we're going to remove x from. And we're going to use our second equation, the one we highlighted, our eliminator equation, to do that. Now, on the left-hand side, here we have 4x. Now, I need to multiply the middle equation by a number so that the 2x becomes 4x. what can we multiply by 2x to get to 4x? 2. So what we're going to do is multiply the middle equation by 2, the whole thing. We're going to multiply it by 2. And this is a scalar, so we're scaling the problem up so that we get 4x. So this here is something I would do on the side, not directly underneath it. So when we multiply this by 2, 2 times 2x is going to be 4x. 2 times negative 3y is going to be negative 6y. 2 times 5z is going to be plus 10z. And lastly, negative 7 times 2 is negative 14. Any questions on how we did this here? Now at this point here, we're going to put this equation under the equation on the left. So we'll have our 4x minus 6y plus 10z equals negative 14. So we did the scratch work there on the side so that we can get the x's to be the same, because that's the one we want to eliminate. That's the one we want to cancel out. Now in our elimination process, we're going to either A, add the two together, or B, subtract the two. Will we add or subtract these two equations from each other? Subtract. Now we can, again, whenever we do this, we can check it to make sure we're doing the correct operation, because if we subtract 4x minus 4x is what? 4 minus 4 is 0. And again, when we do this, it's good to just not cross them out and actually make sure we do the actual operation, because it will tell us for sure, are we doing the right one? Because if we do 4 minus 4 and we do get 0, that's what we wanted. We wanted it to cancel out. We wanted it to become 0. Okay, we're doing the right one. Because if we do 4 plus 4, well, 4 plus 4 is 8. That is not 0, so we don't need to do addition. Now, whenever I do this step, either it be addition or subtraction, I put that sign between each one of our terms. Just as a way to, one, remind me that I'm doing subtraction and I don't just change midway through, but also if we do have double negatives, we can take care of it too. So if we look at our first one, 4x minus 4x, 4 minus 4 is indeed 0, so those cancel out. What we wanted to eliminate has been eliminated. Now we'll work through the rest of it. 2y minus negative 6y. Well, here a negative and negative make a positive, so we have 2y plus 6y, which gives us 8y. Now we move to the next one, 3z minus 10z. It's going to be negative because the 10z is bigger. 3 minus 10 is negative 7z. And again, we could plug the numbers into the calculator, 3 minus 10, and let it do it for us, or we can do it by hand. All right, guys. 12 minus negative 14. Again, the negative and negative make a plus, and 12 plus 14 is 26. Any questions on how we got to this here? So we've done the elimination process once, and we now have one equation with two variables. Well, we still need to do this to the other equation. Now again, just like before, what do we need to do to our 2x? What do we need to multiply it by so that we get 6x? 3. So we're going to multiply the second equation, the whole equation, by 3. And once we finish multiplying the entire equation by 3, we're going to place it underneath the other equation. So again, we're going to multiply, distribute this 3. 3 times 2x is 6x. 3 times negative 3y is negative 9y. 3 times 5z is going to be plus 15z. And negative 7 times 3 is negative 21. Any questions on how we multiplied this through? It'd be nice if we had that kind of money, but a lot. All right. We can talk about it more here in a minute. Let's finish this up first. So any questions on how we got the second equation, second eliminator equation for this here? Any questions on how we got 6x minus 9y plus 15z equals negative 21?
6 and 6 cancel.
Yes. Now, would we cancel them using subtraction or addition? Because 6x minus 6x would be 0. So we would subtract these two here. Now, another way to remember it is if the signs are the same, positive and positive or negative and negative, we subtract. If the signs are opposite, we are going to add.
Also, the 2 plus is all
Right, so if we were trying to eliminate z, positive and positive, we would subtract. Or if we were trying to eliminate y and had those be the same, well, it's negative and negative, we would subtract. But if they're opposite, then we would add. So here, we'll go left to right, 6x minus 6x. 6 minus 6 is indeed 0. It cancels out like we wanted. Negative y minus negative 9y. Well, the second negative makes a plus. So we have negative y plus 9y. Negative 1 plus 9, which gives us 8y. Now we move on to z. 4z minus 15z. 4 minus 15 is negative 11z. And lastly, negative 3 minus negative 21. Well, the second negative makes a plus, giving us 18. Right, it's very tempting to say 24. If we'd had negative 3 plus negative 21, then it would indeed be negative 24. But since we have 21 minus 3, or negative 3 plus 21, it goes down. Any questions on this here? Well, we've done what? We've taken 3 equations with 3 variables. Now we have 2 equations with 2 variables, yes? Our next step in this here is to pick a variable and eliminate it. It's almost the exact same as step 1, except we don't have an eliminator equation. Questions on this so far? Just kind of how we picked x, we're again looking for one of the 2 variables to easily make them be the same so that we can eliminate it out. But this time, instead of picking one of the equations to make be the same as the other 2, we're just looking at the equations themselves. So if we look at this here, x, or not x, but y and z, is one of these 2 variables going to be easier to make the number in front of it be the same? Well, looking at the numbers in front of z, well, one of them is what? 7, the other is 11, yes? Would it be possible, I mean, it is possible Well, what would we need to multiply by 7 to get to 11? Can we do that with a single number? Could we go from 11 to 7? We really don't want to go up or down because we're multiplying by a number. Because we want to go up. Because we don't normally want to go down. We don't want to go from 11 to 7 because we want to make them be the same. Well, what's the number in front of y? How about the other y? Are they already the same? Now, if one of the numbers in front of the variable, especially at this point, is already the same, pick it. Because we don't have to do anything to it. Because with z in this case, I'd have to multiply the 7z by 11, and I'd have to multiply the 11z by 7. I have to do two things. Here, since y is already the same, I don't have to do anything to it. I don't have to do anything to make them be the same so that we can eliminate them out. Which is nice, especially if at the beginning, if one of the variables has the same number in front of all of them, do it first. Eliminate it first. Yeah, you can write it in the middle somewhere, because we will need space to the sides, because we're going to do our next step, which is going to be working backwards. I put the line in the middle at the start as a way to divide the two equations so we don't get those works, how we work to get those two equations with two variables mixed up or interchanged. Now at this point here, we want the y's to eliminate. We want the number in front of y to become 0. So would we add the two equations or subtract? Because we're trying to get y to be 0. So we could add 8y plus 8y. 8 plus 8 is 16. Is that 0 like we want? No. So we can try subtraction. 8 minus 8 is 0. And again, trying it out and seeing which one is helpful, because it makes sure we get the correct one. So 8 minus 8 was indeed 0 like we wanted, so that means we'll subtract. So 8y minus 8y is indeed 0, just like we wanted. So we don't have y anymore. Now z, negative 7z minus negative 11z. Well, our negative makes a. So we have negative 7z plus 11z, or 11 minus 7, which is positive 4z. Now, we could do that in a calculator if we wanted. Do not put the variable. But we could say negative 7 plus 11, which would give us 4. The calculator can do it for us. It just needs a value for the variable. So if you did plug in to the graphing calculator, negative 7 plus 11, or negative 7z plus 11z, it will give you an answer. It's just going to plug a value in for z. If you did not set it, or someone has not set it before, it's understood, or it has it as 0. So it doesn't help. But the last part, 26 minus 18 is 8. Any questions on any of this so far? Now, yes, there are a lot of little steps that we're going from one thing to the next. But again, if you try to tackle this all at once, it is a lot and it's very complicated. But again, with any of these here, take it one step at a time. Because y'all can do this all as long as you take it that one step at a time, one process at a time. Do not try to do this all at once. Because we've started out with 3 equations with 3 variables, went to 2 equations with 2. Now I have 1 equation with 1 variable, yes? Solve. Solve for z. What would we do to solve for z? Both sides by? So we have one part of our solution. Z is 2. So step 3, we can say solve and solve backwards. I've not seen it. I mean, some books or some places might say solve backwards. I have not seen that specifically stated. Because I think even here, substitute the values into step 2 of the original equation, solve. Yeah. But we're going to solve backwards. And what I mean by backwards is we're going back up the page. Because if we look back here, let's focus up here, guys. Because we have z equals 2, yes? If I go back up the page, at this point here, when we had two equations with two variables, when we first came to it, we didn't know what the value of y or z is. But do we have one of those two values now? But yes, we have the value of z. So we need to pick one of these two. Which one do y'all want to use, the left or the right? It doesn't matter which. Yeah, because now I do have one of those two values, yes? So what we're going to do is I'm going to take that equation, 8y minus 7, but we know what z is now, z is 2. I'm going to plug it in and solve for y. We're solving back up the page. We're solving backwards because we're going up. Well, negative 7 times 2 is negative 14. At this point here, we can get y by itself by and 26 plus 14 is 40. And last but not least, we can divide both sides by, telling us y is 5. So now we have two of the three variables, yes? Now we're going to keep going back up. So we found y is 5, z is 2. Now we just need to find the value of x. And when you list the solution, we'll list it as kind of this ordered pair or this ordered triplet as your answer. Now the question is, which equation do we want to use to solve for z, or not z, x? The first equation, second equation, or third equation? Doesn't matter. Third. So this one here? Yeah, because it doesn't matter which, because since this is a solution, it will be true for all three. We plug our values back in. We don't know what x is, so we'll still leave it at 6x. Minus, I know y is 5, plus 4 times 2 is equal to negative 3. So like we did with the second, finding y, we'll do the same thing with finding zx, not zx, by plugging the other two values in. Now at this point, we need to simplify. We can drop the parentheses because we have negative 5. 4 times 2 is plus 8 equals negative 3. Negative 5 plus 8 is going to be plus 3. Next step would be 2 minus 3 from both sides, telling us 6x is equal to negative 6. Yes, we divide both sides by 6, telling us x is negative 1, minus 1. So our solution to this here, our point that works for all three equations, is the point negative 1, 5, 2. So to do this, we started off, we picked a variable to eliminate. We eliminated it out of two of the three equations. Picked a variable to eliminate out of those two. We're left with one, found its value, and then solved back up. Questions on any of this here? This is where we're going to stop for